All right, so first, what is a factor? A factor is one of several quantities multiplied to form a product. All right, so when you talk about like the number 15, 3 and 5 are factors of the number 15. When you learned how to find the greatest common factor, you factored everything into primes, and then you decided how you were going to use each piece of the factors of the two numbers. All right, so this first example that they give us is just like you would have done in taking out the greatest common factor. So the greatest common factor is the product of all the factors that are shared by every term of the polynomial. Two numbers, our terms, are considered relatively prime if their greatest common factor is 1. All right, so greatest common factor is something that you would have used when you look at multiples of things. And then this term right here is more than likely a new term for you, relatively prime, meaning that together they only have a factor of 1. All right, so even if you don't have a prime number, they don't have any factors in common. So like 8 and 15. 8 has factors of 2. 2 cubed is 8. 15 is 3 and 5. If I were to say what's the greatest common factor between those, there is no greatest common factor between those, right? There's nothing that goes into 8 that also goes into 5. So they're considered relatively prime as a group, even though neither one of them is prime on its own. They're not prime numbers, but compared to each other, the only thing they have in common is 1. Greatest common factor is a term that you probably should have used now. So let's look at greatest common factors, all right? For something like 108 and 72, we've done this before. We may not have done 15x and 42x squared y. We're going to look at them individually. All right, so the method that I use is the factor tree. You may have done like a ladder or something else, but you look at 108 and you're going to write it in prime numbers. So you first and say what goes into 108. I usually choose the smallest prime number that I can think of that goes into 108. So like an even number would be 2. 2 goes into 108. And so I would factor it something like this. 2 and 54, 2 and 27, 3 and 9, 3 and 3. I do this so that I don't lose anything in the process, all right? Even if something else can go into it bigger, when you do it inside there, then sometimes you lose your prime numbers in the factor tree. So if I were to rewrite this guy as a prime, I have 2 of those, so it would be 2 squared. And I have 3 of these, so I would say 3 cubed. That's how I would write that in prime factorization. 72. All right, so 72. I am just breaking it down into the smallest numbers I can get it into. Prime numbers, hopefully you know that term. It's only divisible by 1 in itself. All right, and so composite. Composite means we have other numbers that go into it. So 72 is a composite number. And so I want to break it down into primes. All right, and so I am 2 and 3 are prime. So I wrote 108 as 2 squared times 3 cubed. If I were to take 2 squared times 3 cubed, I would get 108. That's how that works, okay? And so I just broke that number down into just prime numbers. It's called prime factorization. So I'm going to do the same thing with 72. It's an even number, so what goes into it? 2 goes into it. How many times does 2 go into it? 36 times. 2 goes into 36, doesn't it? Right. 2 goes into 18. And then we have 3 and 3. So I can write this as a prime factor, right? So I can say, how many 2's do I have? I have 3 of them, so that's 2 cubed. How many 3's do I have? So that's 3 squared. Right? Does everybody see? Okay? Does that make sense? So that's my prime factorization of those two numbers. So if I look at this, I look at the first guy and I say, okay, this one has 2 2's. This one has 3 of them, all right? When I'm looking at greatest common factor, I'm going to use the smallest multiple of those, all right? So the first one only has 2 to take out, so I can't take 3 out and say I can use all 3 of those. So I'm going to go with the one that is the smallest. So I'm going to go with this guy. Greatest common factor, I'll take out the 2 squared. So I'll take out 2 of the 2's. So I can take out 2 of them. All right, they have those in common. Do you see that? They have those in common. 2 2's in common. 2 times 2. All right. I know that he has an extra one, but I can't take that out as a common factor because it's not in common to the other guy. The other guy doesn't have another 2 to pair up with. Does that make sense? I'm looking for what is in common. So I can only take 2 of them out. Yes? So then how many 3's can I take out? I can only take 2 of those as well, right? If I look at this one, he has 2 available, so I can take a 3 out. I can take another 3 out, but I can't take a third one out. Why can't I take a third one out? The guy on the right doesn't have a third one to give me, so I can only take 2 of those as well, so I'm going to have this, all right? And yes, this will have a leftover 3. That guy will have a leftover 2, but I'm looking for greatest common factor, what's in common, all right? And so if I were then to calculate what my greatest common factor would be, it's going to be my 2 2's and my 2 3's. 2 times 2, 3 times 3. So what is my greatest common factor here? It's 36. That's the technical way to find greatest common factor, by the way. What's nice about it with variables is I don't have to factor it. It actually tells me how many I have with a little guy called an exponent, right? And so I don't have to worry about my exponent so much because greatest common factor is easy. It's just right in front of you. So I'm going to look at the numbers first. 15 is also an easy prime factorization. That's 3 and 5, right? 42, 2, and 21, 3, and 7. I only have one thing in common here. What's in common with the numbers? The only thing in common is the 3, so I can take a 3 out. All right? Let's look at my variables then. We're going to first look at the x's. I have 1x here and 2x's here. What do they have in common? An x, and how many of them? They only have 1. Remember, you're going to take the lowest one out because the first one cannot give you 2. He can't give 2. He can only give you 1, right? And so 1x there. Well, let's look at my y's. I have a y here. All right. What's the problem? Is he in common? No. He is not in common. So my greatest common factor here is just my 3x. I am done. Just my 3x. I am done. Let's talk about what's left over. Let's talk about what is left over. So for this one, he has a 5 left over. What about the x? Did we use it? Yes. So he only has a 5 left over. All right. Let's talk about this one. They have a 2 and a 7. So we have 14 left over. What about the x's? Do I have any left over?
1.
I have 1 x left over. What about the y's? 1. I have 1 y left over. All right. That's what would be left if I were to take those out, which is what we're about to do. Now, something else that you're going to notice about these is the word, I want you to know the word divisible, okay? You're really looking for what's the greatest number that is divisible by both, that both numbers are divisible by, rather. So 45 is divisible by 15. If I divided 45 by 15, I would actually get what I had left over here. I would get a 3. So if I took out the 15 with division, I would have a 3 left over. All right. If I divided 75 by 15, then it would be 5. Okay, they're divisible. And so like for the second one, 24 and 32, you may have very quickly seen what your greatest common factor was without having to do a factor tree, because you know both of those are divisible by 8. Here's the thing with divisibility and what we're about to do in the next steps. You have to make sure that you are using the greatest common factor, okay? Because 24 and 32 are also divisible by 4, right? And so if I divided 24 by 4 and divided 32 by 4, I would get 6 and I would get 8. And what you would see is that they still have something in common, right? They have a 2. And so the factor tree helps you see that you have taken every single piece out and gotten truly the greatest common factor. But if you just divide out a number and you see, hey, I can take something else out, divide it back out, you could divide that 2 out as well. You could say, okay, a 4 came out and a 2 came out, so that must be 8, must be the highest one. Does that make sense? And so what we're really looking for is the highest number that they are both divisible by. That is what greatest common factor is. All right, because we're about to use it in factoring, which is basically dividing out the polynomials. All right, so I have 1, 5 here. It has to be a 1-to-1. 1, 5, 1, 5. Okay, I can take him out. They're in common. 1, 3, and 1, 3. They're in common. But this 3 has nothing over here that's in common. Does that make sense? And this 5 has nothing over here in common. We are looking for what's in common, greatest common factor. And so we're just looking for those pieces that come out. One of the first things that we did with polynomials is we did distribution, okay? So distribution would take a number on the outside, and it would multiply what's on the inside by that number on the outside. And so you would take this and you would say 2 times x, 2 times -3, right? And you would do something like that. Factoring is basically the reverse. So think of it when you learned multiplication in elementary school and then you learned division, right? In order to do the division, you needed to understand the multiplication. So in order to do the factoring, you need to understand the distribution, okay? We are basically undistributing, and eventually we're going to unfoil, all right? And so when you take something out, all it means is look for the greatest common factor, divide everything by it, all right? Which is kind of what we've been doing. And so they gave us something very easy. You probably don't need to use the factor tree for these. If I'm looking at 8 and 16, what is the largest number that both of those things are divisible by? 8, okay? And so you can always go over here and you can say I have 2 and 4, and I have 2 and 2, 16, I have 2 and 8, 2 and 4, 2 and 2. You're going to see that you have 1, 2, 3, 1, 2, 3. You have 3 2s in common, all right? If you take a 4 out, you'll see they still have a 2 left, and you can take a 2 out as well. Does that make sense? So when you start getting to, like, and I even tell you that when you reduce fractions, if you can't see the biggest number it will reduce by what you know, and reduce again. So if you see a 4, take a 4 out, you will still have a 2 and a 4. They both have a 2 in common. Take a 2 out, and then you'll see 4 and 2 came out. 4 and 2 are 8. Okay? And so you can easily see that 8 goes into both of these. So I am going to take the 8 outside. So now I am putting a number on the outside, and I'm going to have something in parentheses left on the inside. All right? Parentheses left on the inside. And so when I do that, I have this right here and this right here. I've taken something out, and I'm going to have something left in. Now, when I say you're taking it out, you're literally just dividing everything by it. What's left if you were to factor that piece out of it, okay? So I'm going to say 8 divided by what I took out. 8 divided by 8. What do I get? 1. And I did not take any x's. Why did I not take any x's? Is it in common? Does the 16 have any x's to give me? It does not. So I didn't take any out, so they are both left. All right? We leave this sign exactly what it is. It is a negative. We're going to leave a negative there. And then 16 divided by what I took out. 16 divided by my 8. What is it? 2. And so the factorization of this right here is 8x squared minus 2. Do you think I could possibly check to see if I did that correctly? What do you think I would do? What do you do when you divide? How do you check your division? Long division in like elementary school. You multiply it back, right? And so you can always check and say, did I do it right? 8 times x squared. 8 times negative 2. Yes, I did. All right. And so you can quickly see that, yes, I did it correctly. This is my answer. Now I will say, make sure that is your answer. You don't accidentally tell me that this is your answer. That is your checking, not your answer. That was the question, right? So your answer is actually the factored piece of it. The first step is to find the greatest common factor of all of your terms. Find your greatest common factor. Divide it out. Basically, the distributive property in reverse, right? Write the factorization as the sum of the quotients. So inside you will have parentheses with an addition or subtraction. And then you can check it by multiplying. It's that simple. All right, let's look at these examples. Example 3. Factor 42a cubed plus 14a. Once again, if you do not see the common factor between 42 and 14, you can do your factor tree. All right? You can say 2 and 21, 3 and 7. All right? And then you can say 2 and 7. What do they have in common? They have a 2, right? What else do they have in common? 7. So my greatest common factor between the 42 and the 14 is what? Yeah, it's going to be 14. All right, so we're going to take a 14 out. So 14 is going to be on the outside. What about my variables? Do I have any variables in common? Yeah, an a. How many can I take out? 1. Why, Dustin? Why can I only take 1 out?
Because that's the only type that is not common.
Right. The 42 has 3 A's. That's great. But the 14 only has 1 to give me. And so the most I can take out on the outside is 1. All right. I am now dividing. 42 divided by 14. I just did my factor tree. So there's a really easy way to tell what 42 divided by 14 is. It's going to be whatever I had left over. What did I have left over? Yeah, so this is going to be 3. I started with 3 A's. I took one of them out. How many do I have? 2. 14 divided by 14 is what? 1. I started with 1A. I took 1 out. How many does it have left? It doesn't have any. A divided by A is just 1, so we're just going to leave it like that. That is my factorization. I am done. And you can check it. You can multiply that through. 14a times 3a squared is 42, and a times a squared is a cubed, right? They're getting even bigger, all right? So this one you may not have to use a factor tree because these are very common numbers here. We have 36, 9, and 27. What goes into 36, 9, and 27? 9 does. So had you started with 3, you would see you would have another 3 left, okay? But once again, you can factor them if you want to. But if you look at these 3, 9 goes into 36, 9 goes into 9, 9 goes into 27. So my greatest common factor between my numbers here is going to be 9. Let's look at my variables. I have x squared, x to the first, x to the first. How many x's can I take out? 1. Let's look at my y's. I have y to the first, y cubed, and y to the first. How many y's can I take out? 1. This is going to be on the outside. Let's look at the inside. 36 divided by 9. What's 36 divided by 9?
4.
It's just 4. I started with x squared y. I took out an x and a y. What am I left with? Just an x, right? So I started with 2 x's. I took one of them out, so 1 is left. I started with 1 y. I took 1 out. There's none left. All right? 9 divided by 9, what do I get? 1. I started with 1x. I took 1x out. How many x's do I have? I don't have any left here, right? 2 y's. So I started with 3 y's. I took 1 out, so I have 2 left. All right? Minus 27 divided by 9 is what? 3. I started with 1x. I took 1 out. I started with 1y. I took 1 out. Do I have any variables left? I do not. That is my answer right there. Not all polynomials can be factored. If no common factor other than 1 is found, it is considered prime. So polynomials can be prime as well, meaning that you can't factor them. It's the same meaning as a prime number. Prime number can't be factored by anything except 1. And so if I look at these two numbers, 51 is not a prime number, actually. 3 and 17 multiply to give you 51. 26 is not a prime number. So neither one of these are prime. I can multiply 51 by 3 and 17. Those are my factors there. This is going to be 2 and 13. What's the problem, though? Even though neither one of the numbers are prime, do they have anything in common? They do not. So I cannot take anything out, all right? What about my variables? I have an x cubed and a y. Do they have anything in common? No. They do not. This is prime, meaning I cannot factor it. So if I were to give you a problem and say factor it, and you say, well, there's nothing to take out, you would write the word prime. That is prime. It cannot be factored. All right? There are going to be times, because eventually we will get to this point in this chapter, where you're actually looking for groups that are in common. So if I look at them as a group, so I am comparing this to this when I am talking about what I have in common. Okay? And so I'm looking at the x plus 1, and the 2, x plus 1. So what do they have in common? Yeah, they have this whole thing in common. X plus 1 is in common. And so I am actually going to take the x plus 1 and put it here. And I will still use parentheses to tell what is left over. If I go back up here, what's left over when I take out an x plus 1? For the first one is an x, right? Everybody see I have an x left over there? I took out the x plus 1, so it's gone. And then plus, what do I have out of this group?
2.
Yeah, plus 2. And so I have x plus 1, x plus 2, all right? We're actually going to get to where it's not grouped like this, to where it's actually FOILed out, where it would be like x squared plus 3x plus 2. But sometimes you're going to be looking and taking groups out and factoring that way. Your answer could be x minus 2x plus 8 or x plus 8, x minus 2. What's happening in between the two groups? What operation? Multiplication. So it's like 2 times 3. That is the same as 3 times 2, right? And so it doesn't matter which order you list your group in, as long as the groups are the same. It's just multiplication.